Hi, my name is Brian. As a scientist at MIT, my work is geared towards understanding the mechanical connection between the nucleus and the cytoskeleton. To do this, I use a technique called X-ray crystallography, or as I like to call it, molecular photography. In this video, I will demonstrate how scientists take purified protein that is invisible to the naked eye, like this one, or in some cases nucleic acids. Afterwards, crystallizes them, then shoots them with X-rays in order to obtain atomic resolution structures of how these proteins look inside of the cell, which you have probably seen as these beautiful ribbon diagrams in your book or in Professor Lander's lecture. This technique has proven incredibly invaluable to understanding how the cells work, how diseases develop, and also how to fight against disease. After this video is done, you should be able to explain the basic principles of X-ray crystallography. To explain the basic idea of how X-ray crystallography works, I'm going to use an analogy created by Professor Alexander McPherson. Imagine that you have an invisible object, let's say a car, that has all of its physical properties. How can one visualize it? What if you throw basketballs at it from a specific location? The balls will bounce at an angle specific to the part of the car that was hit. Now let's say that you can move around the car and throw balls from every possible direction and record how the balls bounce off from the car. Depending on the orientation of the car with respect to the ball thrown, some bounces are going to be more favored than others. For example, if you're throwing balls at the front of the car, this will bounce most likely from the hood or the windshield. These observations of how the balls bounce, depending on the direction from which you throw them, provide information about the structure of the object. Using mathematical procedures, one is able to model the shape of the object based on these observations. Now imagine that you use something smaller than a basketball to throw at the car. Let's say, for example, ping-pong balls. Now you should be able to determine finer details about the shape of the car, for example, the rims, doorknobs, wipers, etc. Now imagine that you're throwing basketball at this car from the sky. It would be very, very difficult to see how the balls bounce from this one little car. But what if we have a parking lot full of this particular car, all parked in a symmetric, similar way? Now if you throw balls from one direction, you should be able to record a larger amount of observations, making your analysis of the shape of the car even easier. Now, instead of balls, we have X-rays, and instead of a car, we have proteins. And of course, a crystal is basically a protein parking lot. So how do we go from these purified proteins into these intricate, beautiful structures that you have seen in Professor Lander's class? We crystallize the protein of interest by placing it in a condition in which we'll promote the atoms of the protein to form an ordered, solid structure. Then we shoot the crystals with X-rays and use mathematical analysis to obtain those beautiful structures. You have the opportunity to explore protein structures on your own through the problem set. One structure that you will encounter is of the enzyme lysozyme, which breaks down bacterial cell walls as a defense mechanism against infections. In this video, we will crystallize lysozyme and walk through the steps of X-ray crystallography. So how do we start the process of crystallization? First, you need purified protein. The purer, the better. You can learn more about protein purification in the GFP and beta-galactosidase lab videos. I'm starting with a high concentration of very pure lysozyme in solution. Why do we need to crystallize the protein to determine the structure? Well, we need the protein to be stable with very limited movement. How does the protein in solution become solid crystals? The trick is to lower the solubility of the protein very, very slowly. There are many ways in which one could crystallize proteins, but today I'll be using the hanging drop vapor diffusion method. I am adding the concentrated lysozyme to a drop containing the crystallization solution on a cover slip. Now I'm placing the cover slip on top of a well, which contains the crystallization solution as well. Crystallization takes place in two steps. First, nucleation, and then growth of the crystal. We can promote crystal formation by controlling conditions like the pH, temperature, and salt concentrations, among other things. So what does crystal formation look like? Here we have a time-lapse video of many lysozyme proteins coming together to form a three-dimensional crystal that is ready for diffraction. Notice the shape of the crystals as they grow. So what do we need to do after crystals form? Well, we had to go crystal fishing. Using the microscope, I will select a single crystal, being very, very careful as they are quite sensitive. We want to be sure that we only select one crystal without breaking it. I'm trying to find a drop that contains single crystals instead of crystal showers. Here we have one single crystal. Now I'm checking that the crystal is birefringent, which is the optical ability of the crystal to change color by polarized light. Then we freeze them in liquid nitrogen, and now they're ready for X-ray diffraction. So how do we shoot crystals with X-rays? Here we have a machine that generates X-rays. This is a very small machine in comparison to synchrotrons, which are large holes in the ground in which electrons are accelerated at extremely high speeds and X-rays are harvested from them. I'm loading our crystal on the holder for shooting now. Okay, our crystal is ready for diffraction. I will now shoot the crystals. So what are the results of the X-ray diffraction? Basically, you have X-rays that are hitting your protein and then diffracting. This diffraction pattern is collected as an image. Here we can see an example of a diffraction pattern of lysozyme after X-ray irradiation. This pattern of dots gives us information about the structure of our protein. From this, we can use computer programs to generate an electron density map. Later, we use other programs to help us identify what is inside these clouds of electrons, which will lead to a structure. Now you know what scientists do in order to determine those beautiful, intricate, colorful structures that you have seen in your lecture and that are also going to be very, very useful in your problem set. After this video is done, you should now be able to explain the basic principles of X-ray crystallography. Hope you had a nice time. Hasta luego.